Now let's talk about how do we know when surface tension is important? When do we have to worry about it? So there are two criteria. First one being there has to be a free surface. Because if there is no free surface, there is no surface tension, because we need to have that surface for that force to exist. And then the next thing is, if there is a free surface, the importance is determined by using Weber's number. So the Weber number is a unitless quantity, much like Reynolds number is. So the Weber number is defined as WE, much like Reynolds number is R sub E. Now, where the Reynolds number was looking at the inertia forces versus the viscous forces, Weber's number is looking at the inertia forces. But instead of comparing them to the viscous forces, they're going to compare them to the surface tension forces. And so we can use this to figure out whether or not we have to worry about surface tension. So the inertia forces in this case are represented by the density of the fluid, the velocity squared, times the length. Now this is typically the length of contact with the fluid. So if you were like dealing with a ship, it would be the length of contact at the waterline. And then we divide that by the surface tension force, that epsilon number. And so when we look at this, if we think about it, much like with Reynolds number, when the Weber number is much, much greater than 1, that's telling us that inertia dominates. And if inertia dominates, well, the surface tension forces aren't really all that important. So when the Weber number is less than 1, that means the surface tension is dominating. And so then we have to worry about that. So it's a pretty easy calculation to figure out whether or not we have to worry about surface tension. So let's take a look at this. And let's say that we have a ship. I'll show off my awesome drawing skills. So we have a ship in the water. Let's get this. There we go. So I've got this ship that's moving along through the water. And so let's say the length of contact at the waterline is 100 meters of length. And let's say the ship is moving with a velocity of 6 meters per second. Well, and now what I want to do is calculate out whether or not surface tension is important. So we'll calculate out the Weber number for our ship. So density V squared L over surface tension force. We need to look up a couple things. Typically, we can take water as 998 kilograms per cubic meter. Going to multiply that by our velocity, which is 6 meters per second. We will square that, multiply that by 100 meters of ship length. And now I'm going to look up the surface tension force of water, 0.728 newtons per cubic meter. Now let's check and make sure that our units are canceling out. Well, I'm going to take a kilogram, I'm going to take one of these meters, second squared, that gives me a newton. So the newtons will end up canceling out. I am left with meters squared divided by meters cubed, so those guys will all cancel out. And actually, let's roll that back because I made a mistake with my units. If you notice, kilograms per meter cubed, meters per second. This is a surface tension force. I wrote force per area, force per volume. That's not right. It's force per area. Okay, so let's roll that back once again. The kilogram meter will take about full second squared. That gives me a newton. So that cancels out. And so now I have 1 meter left here, a meter here. Those two is meters squared. And I've got meters to the third here, so that drops it down to a meter. So 1 over meter over 1 over meter, all the units cancel out the way it should. And what I'm left with is 5 times 10 to the 7. So a unitless number inertia forces are way dominating in the system. We don't really have to worry about the surface tension. So let's change the situation a little bit. Now let's say I've got a little water bug. And let's say his length of contact with all of his legs, his linear contact is 1 centimeter. And then let's say that he is moving along at 0.1 meters per second. Now let's calculate it out. Is that important? There's our Weber number again. Just rewrite the equation. So density 998 kilograms per cubic meter. I have my velocity of 0.1 meters per second squared. I have my length of contact as 1 centimeter. And that's 1 meter is 100 centimeters to get the units to work out. It's important to remember to do stuff like that because the unitless number, if the units don't all cancel out, we're going to have a problem. 728 newtons per meter. And if I go and calculate that out, you're going to get an answer of 1. And so that tells me that I have to worry about the surface tension at this point. So there are going to be 3 videos to look at. The first one is kind of cool. It's showing Weber number and microgravity, so it's got little bubbles. And basically, as you're looking at it, you start out with the inertia force is not enough to overcome the surface tension forces. So you've got little droplets that are just bouncing off each other. And eventually, the inertia forces will overtake the surface tension forces, and it'll begin to cause streams and whatnot. The next video will be a video on surface tension. It's a very zoomed in video of a droplet of water that's basically bouncing on another plane of water because the surface tension forces of each fluid can't be overcome by the inertia. What ends up happening is an osmosis process happens, and so some of the fluid is sucked from the droplet into the surface of the water, which causes a force imbalance, which causes the drop of water to shoot up. But then when it comes down, because the inertia forces cannot overtake the surface forces in the water, kind of acts like a trampoline. It's really neat. And the last one is just a picture of some water bugs walking on water, because it's kind of neat, and it just shows that their weight is not breaking the surface tension force.